Hi FADA kids! Today we are talking about our homework from last class, 8.1, and then we're going to start our new lesson for today, 8.2. So have your homework out from last class, and let's take a look at building trees for our basketball problem here. So two teams, A and B, are playing a best of 5 series, and you needed to build a tree to show all the different outcomes. I did my tree top to bottom. If you did yours left to right, that's fine. We'll kind of get to the same place. But remember, we always start a tree in the I'm sitting here doing nothing stage, and then something happens, right? And in this particular case, game 1 happens. So this is game 1 happening. And in game 1, either A or B won the game. We don't have a winner yet because we're trying to do a best of 5, right? And so if you only won one game, we can't tell who's going to be the best. So we'll play a game 2. And in game 2, these are the different outcomes. A or B, A or B. So this is game 2. Okay. Now, again, A has won twice here. But remember, in a best of 5 series, you've got to win the majority of games. And so somebody has to win at least 3 games. Or the first team to win the 3 games is the winner of this. So we don't have a winner yet, but in these various scenarios we've got, we're close to a winner, right? So in this scenario, A is really close to winning it all, and in this scenario, B is close to winning it all. So let's play another game and see what happens. Look at all the different things that can happen. Now, in this scenario, A has won 3 times in a row. You can stop the tree because A has won the series. In this scenario, that hasn't happened. In this scenario, A, B, A, we don't have a winner yet. A, B, B, we don't have a winner yet. B, A, A, we don't have a winner. B, A, B, 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 A, we don't have a winner. Now, B, 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 we stop. We have a winner, right? B won that. That was playing game 3. Now let's play game 4. We don't have to play a game here, but we do have to play a game here. A, B, A, B, A, B, A, B, A, B, and A, B, and we don't have to play another game here because we've already got a winner. Now let's check and see what we've got going on here. A, B, A, we stop. A has won 3 times. A, B, B, we have to keep going. We don't have somebody who won 3 games yet. A, B, A, we stop. A has won 3 times. A, B, don't have a winner yet. A, B, A, don't have a winner yet. A, B, B came from behind. They won. They won 3 in a row there. So they won 3 games. So we don't keep going there. B, A, we have a winner. B, A, B, B, oh, sorry. B, A, B, we're tied. Don't have a winner. B, A, don't have a winner. B, B, we have a winner. So stop. B, A, we're tied. B, B, we stop. B's won 3 times. So let's go back and see the branches that still need to be played, these ones that are tied. So this needs to be played. 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 And this needs to be played. So that last round was game 4, and these are the only scenarios where we would go to a game 5, the tiebreaker game. And game 5, these outcomes, that's the end. We stop at game 5, right? It's a best of 5 series. So we don't necessarily have to, indicate to ourselves to stop the branch. As long as we continue the branches that need to be continued, we've completed our task of constructing a tree diagram showing all possible outcomes. Okay, so if you need to pause the video and take the notes on this, go ahead and do so. And again, if you did left to right, you would just sort of turn your head 90 degrees and take a look at it and make sure that you matched. Okay? All right, let's take a look at the second problem we had for homework. Now, you throw a dart at this board, and assuming the dart actually hits the board, what's the probability you'll hit region 2 as compared to the others? Now, a lot of you said 1 and 3. There's 3 sections. That means I'm hitting 1 out of 3. But take a look at the board again. Section 3 takes up half the board. Sections 1 and 2 only take up a fourth of the board. So you have double the chance of hitting 3. So there's a couple of different ways to look at this. I looked at it as, well, if I look at this thing divided into sections like this, there's a 2 in 4 chance of hitting section 3, a 1 in 4 chance of hitting this section, and a 1 in 4 chance of hitting this section. So the answer to the question about region 2 is 1 in 4. Some of you said, well, this is 50%, this is 25%, this is 25%. But as long as you don't have a 1 in 3 answer, you should be good to go with a 1 in 4 or a 25% chance. Just be real careful about the situation, the reality of the situation that you're looking at. Okay. All right, now our challenge homework problem is we had these concentric circles. We had this Venn diagram here. Now, I divided this up into Spanish in here, math in here, and chemistry in here. If you had different circles labeled differently, you'll have things in a different place, but hopefully we have the same numbers. Now we're supposed to find the most center population first and work outward for these. So you should have first noticed that 15 study all 3 subjects. So 15 students go in the center where they're all covering each other, overlapping. Then you can choose to go to the only Spanish and math, only math and chem, only chem and Spanish sections. But when you do that, let's take a look at Spanish and math. So Spanish and math and Spanish is here. 20 study math and Spanish. You need to notice that if 20 study math and Spanish, that's this entire overlap here. Okay? We're saying the Spanish and math overlap includes 20 kids. And so if we've already got 15 in this section, that means we put 5 in this section. Okay? For a total of 20 studying both Spanish and math. 15 of them also study chem, but 5 of them don't study chem. They only study Spanish and math. Okay? So make sure that you have that concept in your head. There was 5 here and 15 here. Spanish, math, chem. And apply that to the remainder of the overlaps. So let's look at Spanish and chem next. Spanish and chem, that's 18. So Spanish and chem, that's this cross section here, right? So these sections here, total 18. So that means we should have 15 total, 15 already in here. That means 3 go in here, okay? So 3 go in here. And then the last overlap we have is a chem and math overlap. Chem and math, that's 75. So 75 in this chem and math overlap. That means there must be 60 that just take chem and math and not Spanish. Now let's keep going out even further. If 93 kids study Spanish, this whole circle of Spanish includes 93 kids. So the kids that only take Spanish and not anything else is 70. So this whole circle has to have 93 kids in it. It already had 23 kids in it. So you have 70 left that only take Spanish and neither of the other 2 subjects. Apply the same thing to math. 165 kids study math. This whole math circle has to include 165 kids. Right now, it only includes 80 kids, these 80 right here. So it must be that we have 85 kids studying just math and neither of the other 2 subjects. And then finally, the chemistry statistic. 95 study chem. The chem circle currently includes, 68 kids. So we have 17 left over of the 95 that study chemistry, 17 that only study chem and not Spanish or math. And then we further back out to the box, we had a total of 260 kids to begin with. If we add up all the numbers, take a moment to add up all the numbers and figure out how many kids are taking these various combinations of subjects and see if that gets to 260. When you do that, I added them all up and I only had 255 kids represented in the circles. So that must mean that out of the 260 kids, 5 of them don't study Spanish, Chem, or math. All of that so that we can answer these 3 questions. So, what is the probability of a random student just taking Spanish? The just taking Spanish kids is 70. So 70 out of 260 is the probability of that happening, which is 7 out of 26, or 27%, whichever you prefer. What's the probability of getting a kid that takes math and chem but not Spanish? Math and chem but not Spanish. That's represented here with the 60. So 60 out of 260, which is 6 out of 26, or 3 out of 13, or 23%. Okay? So just a little bit less than the kids taking Spanish. And then none of these subjects, we said that was the number 5, so 5 out of 260 kids, or 1 out of 52, or about 1.9%. So not very many. A very small percentage don't take any of those. Okay? So that is how you did your 3 homework problems. If you need to pause the video and take a break, go ahead and do so at this point. Now let's turn to the warm-up from this morning. Hopefully this went fairly quickly. Which of the following states that the more times you run an experiment, the closer your results will be to the theoretical probability? So experimental probability going to theoretical probability, that's the law of large numbers. The law of large numbers says you run an experiment over and over and over and over again. The more you run the experiment, the closer your experimental probability will be to the theoretical probability. Question 2, the probability of an event occurring is always between, it's always between 0 and 1. 0 possibility to 1%, 0 probability to 1 probability. 1 is absolutely positively will definitely happen. The probability of an impossible event is 0. And the sum of all possible outcomes of an event is 1. They all add up to 1. Okay? So hopefully that went fairly quickly. So let's go ahead and go to the new lesson for today. Independent events. Independent events basically means that if A and B are independent, then the outcome of one of the events doesn't affect the outcome of the other. Okay? Doesn't affect the occurrence of the other event. So for example, the outcome of flipping a coin 2 times. If you flip the coin once, let's say you get heads or tails, that has no impact on what you'll get the second time. Absolutely no impact. If you flip heads, that doesn't mean that you can't flip heads again, right? So that means the two events are independent. Dependent, on the other hand, events A and B are dependent if the occurrence of either event does affect or affects the probability of the other event. So think of the outcome of selecting 2 cards from a deck without replacing. Let's say you pull an ace from the deck first. That means you have a smaller chance of pulling another ace because you've removed one of the aces. Okay? If you're not putting the card back, you're removing one of those chances. So the impact, the first thing you did by pulling that card, that has an impact on your chances of the next card that you pick. So those are dependent events. The probability of 2 independent events occurring is the probability of the first one times the probability of the second one. And we talked a little bit about this last class. The word and. The probability of A and B happening is the probability of A times the probability of B. So and means times. And means multiply. Okay? So for example, if we select 2 specific cards from a deck with replacement. So if you, with the probability of taking a first, and again this is with replacement, if the probability of taking the first ace, so there's 4 aces out of 52 cards, and then with replacement we put that ace back in there. So the probability of pulling another ace is 4 out of 52. This is the probability of pulling the first ace. This is the probability of pulling an ace again. Because we put the card back in the deck, we still have a 4 out of 52 chance. If we multiply those together, and if we reduce that fraction, it's 16 over 52 times 52. That comes down to 1 over 169. So if we multiply these together, we'll have a 1 in 169 chance of pulling 2 aces. Okay? This link will take you to an ice cream activity where you combine flavors of ice cream together. We'll probably do that on review day, but it's a great way to visualize the probability of getting one flavor and another flavor on the same ice cream cone. But really what I want you right now to think of as if you have probability of one event and another event happening together, you multiply them together. Let's take a look at this next probability of 2 dependent events occurring. So if A and B are dependent, then you have this given scenario. Okay? So probability of A and B happening in a dependent scenario is something like selecting 2 specific cards without putting them back, right? So if you think back, we just talked about this a second ago. It's dependent. The probability of selecting a first ace is 4 out of 52. But if you don't put that ace back, you only have 53 cards in the deck, and you only have 3 aces left in the deck. Oh, sorry, that's a 51. Can't subtract. Sorry, you have 51 cards left in the deck, and you only have 3 aces left in the deck, because this is a dependent scenario. The probability of pulling that second ace is dependent on the fact that you pulled an ace the first time and didn't put it back. Okay? So the dependent scenario is slightly different than the independent scenario. So when you multiply this together, you get 12 over some gigantic number. That simplifies down to 1 in 221. So if you compare that with replacement, you had a 1 in 169 chance. But without replacement, you have a 1 in 221 chance. And that makes sense, right? You pull an ace and you don't put it back, your chances are smaller of getting a second ace. Whereas if you put it back, your chances are larger of getting 2 aces. They're still not great, but they're larger. Okay? So make sure you understand the difference between independent and dependent events. So let's flip the page and look at mutually exclusive events. Mutually exclusive means that events A and B can't happen together. It's not possible for them to happen together. If it's not possible for 2 outcomes to happen together, they are mutually exclusive. So for instance, if you're picking a card from a deck, the outcomes of that card being a king and at the same time being an ace, that's impossible, right? You either have a king or an ace. You can't have both. So that means that is a mutually exclusive event. Okay, pulling a card and having it be a king and an ace is mutually exclusive. When it's mutually exclusive, we often have to answer the question, okay, it's mutually exclusive, but are those events complementary? Complementary means those 2 mutually exclusive events are the only 2 possible outcomes. So for instance, heads and tails of a flipped coin. If you flip a coin, it's either heads or tails. It can't be both. So the heads and tails outcome are mutually exclusive. And since heads and tails are the only things that you can get, it's not like you can get heads or tails or Skittles, right? There's no third option. Since heads and tails are both mutually exclusive and the only 2 possible outcomes, they are also complementary. To calculate the probabilities of mutually exclusive events, we'll take a look and see what we mean by this. So the probability of A and B happening of mutually exclusive events, that's impossible. Just like the heads and tails. Getting heads and tails, that's impossible. Right? Probability of an ace and a king, that's impossible. But the probability of A or B occurring for 2 mutually exclusive events, well, that's calculated by finding the probability of the first one happening and adding it to the probability of the second one happening. So instead of and, we have an or, and or means add. So and means multiply, or means add. Okay? So for instance, pulling a club or a heart. You can't pull both, right? You can't pull a card that has both club and heart on there. They're mutually exclusive. But the probability of pulling a club or a heart, that's the probability of the club plus the probability of the heart. Well, let's think about that. What is the probability of pulling a club? Well, there are 13 cards in the deck that are clubs. What's the probability of pulling a heart? Well, there are 13 hearts in the deck. So the probability of pulling a club or a heart is 26 out of 52, which can be reduced down to 1 over 2. 1 out of 2, or 50%. Okay? Now, what if you've got events that are not mutually exclusive? Probabilities of events that are not mutually exclusive. To calculate those, the probability of A or B happening, we have to take into account, not only do you have to find the probability of A happening plus the probability of B happening, but there's a chance that they can both happen, right? There's a chance that both of them can happen because they're not mutually exclusive. You could have A and B. So we have to take the probability of A happening plus the probability of B happening and subtract out the probability of them both happening, A and B happening. Okay? So the probability of pulling a club or an ace. These are not mutually exclusive. You could get a card that is both club and ace. Okay? So to calculate this, we say, all right, what's the probability of pulling the club? Add it to the probability of pulling an ace, and subtract out the probability of pulling something that's a club and an ace. So the probability of pulling a club, there are 13 clubs in the deck, plus the probability of an ace, there are 4 aces in the deck, and then subtract out the club and ace scenario. Well, how many ace of clubs are there? There's only 1, right? So subtract out 1 out of 52. So that leaves us with 13 plus 4 minus 1. 13 plus 4 is 17. 17 minus 1 is 16. So there's a 16 in 52 chance of pulling a club or an ace. And we can reduce that to 4 out of 13. Okay? So that's for events that are not mutually exclusive, for things that could happen at the same time. Our last terminology of the day will be conditional probability. So when the probability of an event is affected by the knowledge that the other event has occurred. So this is another given. Okay, so the probability of event A given that B has occurred. So the terminology or the notation for this is probability of A given, this bar right here says given, B has already occurred. Okay, so the probability of A given B happened first. That's what that means. So for instance, you roll 2 fair dice. What's the probability that the sum of the dice is 5 given the first die roll was a 2? All right, let's slow this down. We're trying to say what's the probability the total on your dice is 5 given that the first roll is a 2. To calculate this, we say, what's the probability of the total being 5 and the first being a 2? Once we have that, we divide out the probability that the first is a 2. We know how to do this one. The probability of the total being a 5 and the first being a 2, that's a multiplying. And means multiply. What's the probability of the total being 5? Well, what's the probability of the first being a 2? The first being a 2 is 1 over 6. How many different ways can you total 5 if you first rolled a 2? If you roll a 2 and you have some other second roll that you need to add to it, and they need to equal 5. How many different ways could you make this happen on that second die roll? You can only make that happen one way. You can only make that happen if you roll a 3 on that second dice roll. So there's only a 1 in 6 chance that that's going to happen. So there's a 1 in 6 chance that you roll a 3 after the 1 in 6 chance of rolling a 2. So that's that event happening together. And then we divide out the probability that the first is a 2. So that's 2 events. So 1 out of 6 times 6 out of 6 is the probability that the first was a 2. So the top fraction becomes 1 over 6 times 1 over 6, so that's 1 over 36. And we're dividing 1 times 6 on the top and 36 on the bottom. Remember what happens when you divide fractions? Hopefully you remember from earlier grades. 1 over 36 divided by this fraction is the same thing as multiplying by the flip. So cross this out, and we get a 1 in 6 chance. So the probability that the sum of the dots is 5, given that the first die roll is a 2, that's a 1 in 6 chance. Alright, this is definitely the most complicated you'll see. You may not even see anything that complicated on a quiz or test, but definitely you will see this notation here of the given. This means the probability of A happening given B already happened. Okay? So let's go back and analyze this vocabulary we just learned. Let's look at some events and identify whether they're dependent, independent, or mutually exclusive. And if they're mutually exclusive, we need to say if those are complementary. So let's take a look at the first one. An NFC team wins the Super Bowl, and an AFC team wins the Super Bowl. Are those dependent, independent, or mutually exclusive? Hopefully you said they're mutually exclusive, right? You can't possibly have an AFC team and an NFC team win the Super Bowl. It's either one or the other, right? So that's mutually exclusive because they can't happen together. Those are mutually exclusive events. It's either one or the other, right? That the Super Bowl is an AFC team versus an NFC team. And then now that we've said that they're mutually exclusive, we have to say whether or not they're complementary. Are those the only 2 outcomes of the Super Bowl? The answer to that is yes, those are complementary. Because you can only have, the end of the Super Bowl is either AFC 1 or NFC 1. So those are complementary since those are the only 2 outcomes of the Super Bowl. Okay? So let's look at number 2. The Redskins win the Super Bowl and the Washington Wizards win the NBA championship. Are those dependent, independent, or mutually exclusive? They have nothing to do with each other, right? They have nothing to do with each other. So those are completely independent events. Unless it's the same person paying for the teams, right? Those are completely independent. It has nothing to do with each other. So those are independent events. The Skins win the Super Bowl and DC has a parade to celebrate the win. What are those? Independent, dependent, mutually exclusive. Those are dependent, right? They're dependent events. We're not going to have a parade about winning the Super Bowl unless we win the Super Bowl. So those are dependent on each other. Number 4, the first 2 numbers of your pick 3 Lotto match the winning numbers and the third number does not match. So picking those numbers, if you pick those first two numbers win, but the third number does not. Is that independent, dependent, or mutually exclusive? It's definitely not mutually exclusive. Those certainly are not the only 2 outcomes. Or those certainly don't impact each other. They are independent, they're independent, right? So independent, your picks of the first 2 numbers have 0 impact on whether the third one wins or not, right? It's not like you've limited your choices of numbers that you could use in the end. So picking those first 2 numbers has nothing to do with whether the third number wins or not. So those are independent events. And then finally, if Gus takes the bus to school, so Gus taking the bus to school and Gus receiving a speeding ticket on his way to school. What do you think about that? Gus taking the bus to school and Gus receiving a speeding ticket on his way to school. Those 2 events are mutually exclusive, right? You can't have both. If you're taking the bus, there's no way you can get a speeding ticket. If you're getting a speeding ticket, there's no way you took the bus. So those are mutually exclusive events. They can't happen together. They cannot happen together. And the question is, are they complementary? Are these the only two potential outcomes of this event? Absolutely not, right? He takes the bus or he drives to school. Just because he drove to school doesn't mean he gets a speeding ticket, right? He could drive to school and not get a speeding ticket, right? So there are 3 or more possible outcomes of this scenario. So while these two events are mutually exclusive, they can't possibly happen together, they're not the only two situations. They're not the only two events that could happen in this situation. Okay? All right, so that's honing down our vocabulary of the day. Let's take a look at some examples of how to use this vocabulary. So if you roll 2 paired dice, and if you need to pause the video and take a break at this point, that's fine. Go ahead and pause and take a break. But if you're back and you've finished pausing the video, practice problem number 1. You roll 2 fair dice. What's the probability that a 4 shows on each die? A 4 showing on each die. Well, what's the probability that a 4 shows on the first roll? On the first roll, there's a 1 in 6 chance that you get a 4. What about the second die? Well, the second die has nothing to do with the first one. And we're talking about a 4 on the first die and a 4 on the second die. So, and the first one being a 4 and the second one being a 4, that means we multiply. And the probability that a 4 is on the second die is, again, 1 in 6. So if we multiply these together, 1 times 1 is 1, 6 times 6 is 36. You have a 1 in 36 chance that you get a 4 on both die. And if you want to convert that to percentages, that's fine. Let's look at practice problem 2. So these are dependent events. The first one was independent. The rolling of 4 on the first die had nothing to do with the roll on the second die. But now we're looking at something where the events do have an impact on each other. You pick 2 cards from a standard deck of 52 without replacing the first. So since you didn't replace the card, you're going to have an impact on your second card draw. So the first card draw, what's the probability that both cards are red? Both cards are red. So how many red cards are there in the deck? There's a total of 26 in the deck. So the first card pick, I have a 26 out of 52 chance. But then I don't put that card back, right? I don't put that card back. So what's the probability of pulling a red and then another red if I don't put the card back? Well, if I don't put the card back, I only have 51 in the deck. Now, if I pulled a red on the first try, there's only 25 reds left to pick from. So pulling a red and then pulling another red in this dependent event if you multiply those out, you could reduce that down to 25 over 102, or it's approximately 25% if you run that through your calculator. And you can give me percentages if you'd like. But since those are dependent events, the first thing happening had an impact on the second thing happening, we multiply those together, we reduce the possibilities here. Okay, so make sure you're clear about what you're being asked and what's happening in this scenario. All right, practice problem 3, I'm talking about independent events again. So if you spin this spinner around this, the spinner, if whatever you spin on the first spin has 0 impact on what you get on the second spin. So that's why they are independent events. And this is fair. We're assuming there's no sticky points. There's equal chance of hitting any of these. The pointer's spun twice. Determine the probability that the pointer lands on 2 both times. So hitting a 2, hopefully you see that there's a 1 in 4 chance of landing on 2. And then if we want to land on 2 again, so 2, and we have a multiply, that's another chance of 1 in 4, 1 in 4 chance. Okay, so the probability of getting 2 times in a row is 1 in 16. 1 times 1 to the top and 4 times 4 on the bottom. If you want to turn that into a decimal, that's fine. Now let's look at question B. An even number first, and then the number 4. So an even number, looks like there's 2 chances of hitting an even number. So there's a 2 in 4 chance of doing even on the first one. And doing a 4 on the second one, there's only 1 chance to do that, so 1 in 4 chance. So that will leave you with 2 times 1 on the top and 4 times 4 on the bottom, or a 1 in 8 chance of spinning an even and then a 4. And then finally an even number and then an odd number. An even number, we already said this, it's a 2 and 4 because there's 2 of them. And an odd number, there's 2 of those, so that's a 2 and 4. So you get a 2 times 4 over a 4 times 4, which reduces down to a 1 in 4 chance. Okay? All right, let's take a look at another way we can look at these things. We're doing a taste test, and we've got males and females. At a local mall, there's 200 total people. We've got people who prefer Coke and people who prefer Pepsi. If we randomly select somebody from this group, let's talk about what's the probability that they prefer Coke. So the person, whether they be male or female, prefers Coke. The total people that prefer Coke is 85, and the total people in here is 200. Okay, so if you want, we can reduce that down to 17 and 40. The probability that the person is a male, well, there were total 91 males, so your probability there is 91 out of 200 that you're going to get a male. Is a male and prefers Coke, well, that's something different, right? Males who prefer Coke is found in this quadrant, so that's 51 out of 200. Prefers Coke given that the male is selected. So this is a little bit different. Careful on the wording on this one. So given that we're in the male grouping, there's only 91 total males. So out of 91, what's the probability of selecting a male that prefers Coke? So there's 51 of them that prefer Coke. So be careful with this wording. If you see given that a male is selected, that means that you've already reduced your group down to the males only, and then you have to go find how many there are. Similarly, prefers Pepsi given that a female is selected. So we've reduced our group from 200 down to 109 females. So out of the 109 females, how many prefer Pepsi? That is 75. So 75 out of 109 is your probability that you're going to get somebody that prefers Pepsi. Okay? So that's how you use those tables and how you translate these words into your answers. All right, let's take a look at the challenge problem before you have a chance to work on your homework. The reason I call this challenging is because we've got all these givens and subsets of people, and it's a pretty challenging problem. So let's look at it. A local college, 85% of incoming freshman nursing students are female and 15% are male. Recent records show that 70% of entering female students will graduate with a bachelor's in nursing, and 90% of male students will graduate with a bachelor's of nursing degree. If you randomly select an incoming freshman, we want to know the probabilities of A, B, C, and D. Now, I'm not actually going to work these out for you. I want to talk about them when I get back, but I will help you fill in this table. So let's fill out this table to help us understand what we've got going on here. So we've got graduates and getting their degree, and then we've got people who don't get their degree, the no grad group. And then we've got the totals. And we've got male, and we've got female. And we've got totals. Okay, and obviously all totals should be 100% if you add them together. I'm not going to put the percent sign anymore because I kind of run out of room when I do that. But if we say that out of this group 15% are male and 85% are female, that means 15 goes here. 15% are your total males and 85% are your total females. And if you add those together, you have 100. And then it says 70% of females graduate with a degree. So 70%, and that's 0.7 if you're on your calculator, times the 85% that are female will get you your 59.5% graduating females. Okay, 59.5% of the whole group are females that graduate. Because 70% of the 85%, so you're both 70% going to graduate, times 85%. So these two events are happening together. You're female and you're graduating, or rather backwards, you're graduating and you're female. That's multiplied together. Those two events are multiplied together to get 59.5%. Now we could do the same thing over here, but it's easy enough to say, well, 59.5% of the 85 are graduating. That means 85 minus 59.5 aren't graduating. So that's 25.5% of the whole group. Let's go talk about the males. 90% of the males will graduate. So 90% of this 15% of the population. So 0.9 times 0.5, 90% times 15%. Hopefully on your calculator you worked out that that's 13.5% of the whole group. And then easy enough, 15, if you aren't graduating, it's just 15 minus the 13.5, right? There's only a yes-no scenario here. If you're not graduating, then you land in this bucket. 15 minus 13.5, there's only 1.5% of this whole group of males not graduating. So if we add this down, that means of the whole group, 73% graduate and 27% don't graduate, whether you're male or female. Okay, so that was pretty intense. If you need to, you can always pause the video and look back over it. I would like you to start answering these questions as part of your homework and then continue on to your independent practice 8.2 to finish off your homework for the rest of the time you're here. And I will definitely have the keys posted if you want to check your answers, but definitely use the rest of your time to work on your practice so that we're prepared for the quiz next class. Thanks.